So now let's take stock and write down exactly all the things that we have learned. So, effects in special relativity. So suppose we have a frame S and a frame S prime in relative motion with, let's say, the relative motion being along the x direction, which happens to be aligned for the S and S prime frames. Now, the few things that we've learned today is, one, clocks in the moving frame arranged perpendicular to the direction of motion. That is, if I consider the clocks of S prime, so these are various clocks in the frame S prime is moving to the right, then the clocks here all appear to be in phase. So these clocks will be in phase with each other. And similarly, the clocks here will appear to be in phase with each other. The clocks here will appear to be in phase with each other. However, the clocks which are along the direction of motion, okay, clocks placed along the direction of motion will appear to have a phase offset of delta t prime is v L prime over c square, where L prime is the separation between these clocks along the direction of motion. Okay, so let's write this down. So this is the perpendicular separation, okay, perpendicular separation, and this here is the parallel separation. The other thing that we saw is that lengths of rods perpendicular to the direction of motion appear unchanged. However, the lengths of rods parallel to the direction of relative motion appear to be contracted. By a factor of the square root of 1 minus v square by c square. So that is, if the separation between these clocks is L prime in the rest frame of the clocks, that is in the frame S prime, and these clocks are moving to the right, to the ground observer it would appear that the separation between these clocks is L prime times the square root of 1 minus v square by c square. And finally, we saw that the moving clocks, that is the clocks, all these clocks are moving to the right, and all these moving clocks tick at the same rate. But this rate appears to be slower than the rate at which the ground clocks are ticking. Okay, so the important point is these clocks appear to be slower as seen by the ground observer on their synchronized clocks. When they time the moving clocks with their own clocks, they see that the moving clocks appear to be slower. If they take any one moving clock, let's say this one, and watch it as it moves to the right, it would appear to tick more slowly. Okay, so all the moving clocks appear to tick at the same rate, but this rate appears to be slower than the rate at which the clocks on the ground are ticking by a factor of again 1 over the square root of 1 minus v square by c square. So to be precise, if a time interval delta t prime has elapsed on the moving clock, the time interval delta t prime that's elapsed on the moving clock will be longer than the time interval elapsed on the ground. The time interval elapsed on the ground is delta t, and will be smaller than the time interval elapsed on the ground clocks, and the relative factor would be 1 over the square root of 1 minus v square by c square. So this is time elapsed on a single moving clock. And you have to be careful with how you interpret what this time is. So that moving clock moves to the right. You time it with a clock on the ground over here, and you time it with a clock on the ground over here, and these clocks are synchronized. And the time interval between these two clock measurements is what we call delta t. So this measurement is made with two different clocks on the ground, two different synchronized clocks. Whereas this time interval is measured with a single clock on the train, in the moving frame. And we're saying that delta t prime will appear to be smaller than the time interval delta t that has elapsed on the ground. And these 5 effects, okay, the effect of lack of phase synchronization, or lack of phase synchronization for clocks arranged perpendicular to the direction of motion, clocks in the direction of motion appearing to have a phase offset, lengths of rods perpendicular to the direction of motion appearing to be unchanged, lengths of rods parallel to the direction of motion appearing to be contracted, and all the moving clocks appearing to tick at a slower rate compared to the ground clocks. These effects are all consequences, simple consequences of the postulates of special relativity. And the only major place where special relativity makes a break with Galilean relativity is in assuming that the speed of light is a constant as seen by all inertial observers. And this one difference in postulate leads to an amazing array of consequences.